Alright, hey guys, this is gonna be just some last minute pointers before the quiz. And I just want to make some corrections to some things I might have said during the review session for those of you who went. For the review session, some of my numbers were probably not correct, as some of you pointed out afterwards. I don't have a copy, unfortunately, of what I wrote down during the presentation. So I can't give you exact details, but if you think that a number is wrong, work it out and check yourself, and you should probably find. I think I got my reactions wrong for the case with the distributed load and the point load together. Most of them should be accurate, and I hope they're accurate. But there are a couple of mistakes in there. Yeah. Okay. So I'm determined to make sure that you guys leave this class knowing how to draw diagrams by inspection. And I don't know if you've taken a look at the solutions yet online for tutorial 5. You still need equations for you. The professor is expecting equations. Half the credit is basically going towards getting equations down correctly. But being able to look at a system and being able to draw its diagrams without calculating equations is a very valuable skill, and especially for checking your work, for figuring out whether or not a solution you have is even correct. And I just wanted to emphasize that a little bit with a few examples. I think most of you are okay with point loads. Very basic, but I always want to use this example because it's a very basic example, and it illustrates a lot of key points. Where you have your actions are p over 2. Now when you draw your shear moment diagrams, I've been saying this for a while now, but you always want to follow your arrows. Just follow your arrows and everything will work out. What do I mean by that? What I mean is if you start here, always start at 0. You're going to start at 0 and you want to end at 0, regardless of what your boundary conditions are, regardless of the fact that you have reactions here. Just ignore that for a sec. Just start at 0. And always just follow your arrows. So what I mean by that is, you see I'm starting at 0 and I say, oh, right here I go up by p over 2. So I'm going to go up by p over 2. I'm going to go all the way over here. Then I'm going to go down by p. So this is down by p over 2 and down by p over 2. And I keep going all the way across because I have nothing here, right? I followed my arrows here. I went up here. I had no arrows, so I did nothing. I had an arrow here, so I went down here. I have no arrows here. No arrows here. So it's constant. And then I go up by p over 2. So I go up. And I go down, I go up again, I go up by p over 2, I go down by p, this is p, and this is p over 2, I go up by p over 2. If I'm going backwards, if I'm going from right to left, I just do everything in reverse. So let me use this. If I'm going backwards, I'm starting from here. Instead of going up by p over 2, I go down by p over 2. Let me draw neutral axis here. So everything's different, that's fine. I go down by p over 2. So I start at 0, and I go down. Then I go across, because there's nothing here, right? Then I go up by p, because it says to go down by p, but when I'm going from right to left, I do everything in reverse. Just like when you have your, when you take a cut from the right, your shear is this way, your moment is this way, and you take a cut from the left, or on the right to the left, your shear is this way, and your moment is this way. Notice how the shear arrows switch. That is why you do the opposite when you over here. So you're going down by p over 2, you're going up by p, and you're going down by p over 2. I'll illustrate that again. You're going down by p over 2, you're going up by p, and over here you're going down by p over 2. And that is like very quickly how we just drew the shear diagrams without calculating anything. You're like, oh, okay, that's all good and dandy. But then, how do we use this for the quiz? The quiz is not going to be like this. It's not going to be this simple. You're probably right. It'll probably be more complicated, but if this is a very basic principle and you can apply it to anything. I'm gonna go into more complicated example, but I just want to show you how to do moments really quick. So let's start off down here, and let's look at our shear diagram again. I'm not going to look at the moment diagram at all. I'm not going to look at the original diagram at all. I'm just going to say that this is my shear diagram. Okay, and then to calculate my moment diagram, what I'm going to do is I'm going to look at specific points. So let me label this. This is my shear diagram. And by labeling specific points, what do I mean? I'm going to, this way is M positive and negative. I'm going to label this point, and this point. And you're saying, well, what's special about these points? Well, over here, remember that your moment is the integral of your shear. So what does integration represent? Integration represents the area under a line, right? Area under an equation. Like if I have, this is just an aside here. If I have some randomly defined equation, and I want to take the integral. If I take this is defined on from 0 to some point A, and this is some equation y equals f of x. If I want to find the total area of this, I just integrate the equation, right? It doesn't matter how complicated the equation is. Like a more complicated equation will be hard to integrate, but I just integrate. So area equals. Or I should go the other way around. The integration is just the area. Right? It doesn't matter how complicated the integral is. If I can get the area of this somehow, then I'm okay. And I can get the area for my moment diagram pretty easily, right? Because these are just two rectangles, and the area of rectangles is very simple. If this is some length, L over 2, this is some length, L over 2, and this is some height, P over 2, and this is some height negative p over 2. Do you agree that if I start from here and I go to here, the area between these 2 points is 0, right? Because I have a height of p over 2, but my base is 0. So I start off at 0. And then going from here to here, I have picked up an area, right? I have picked up an area of p over 2 times L over 2, or PL over 4. So and remember my positive axis is downward, so I am increasing all the way down to PL over 4. And then over here, it's the same thing but minus, right? It's below the curve. The same exact dimensions. So the area of this, or area of this minus the area of this, is just going to be 0. Because I have p over 2 times L over 2 minus p over 2 times L over 2. So it's just going to go back up to 0. And then the last bit is, what is the shape of this? Is this linear? Is this quadratic? Is this cubic? Remember that it's just an integral. If this is a straight line, that means that we have a constant here, right? So my v of x equals p over 2, or negative p over 2, and this is for x. X less than L over 2, x greater than L over 2. Right? Like this is just it's just a constant. What happens if I integrate a constant? I get a constant times x. And a constant times x is to the 1 power. So x is a linear function, right? Like p over 2. This is the integral of my shear, equals p over 2x equals px over 2. And this is just a linear function. So my relation between these two is just going to be linear. Okay. Now I'm gonna make these videos in a series so you can follow one example to the next and just choose whichever example you need the most. But we're gonna go a step up from this in the next one.